good morning on my behalf also. So I'm actually standing, standing in for our VP2 VP leader Natalie Fleyes, who was unable to come here. But basically, yesterday we discussed quite a lot about specific safety systems of SMRs. So in our second work package, we were trying to basically bring this kind of like more holistic view on things. So I will be focusing on trying to discuss how this when we bring these safety systems into their like whole plant, how does this integrate and what are the considerations here on a bit like a more systemic level. So at least I will be trying, and I of course hope that you will be commenting, asking questions, and of course since we have quite more experienced people than me also in the audience, so I will be looking forward for your corrections, whatever I might say here. But anyway, so okay, I guess this one is not working.
No? Do you think it's possible to just use full screen for the slides?
That's on the Marco, like for the take.
Like the little 2 microns on top of the page, they really add that much into things.
Yeah. Oh, okay. This and okay, now it works. Thank you. Yeah. So, well, as you already heard many times, basically this kind of design of laboratory SMRs aims to have be on the power level, power density, in which we can do many things with passive safety features that rely on natural convection and so on. And the idea here is this to use this to improve safety by limiting the needs for support functions for different kind of active components, suppressing or even eliminating some potential accident modes. If you don't have boron in your core, you don't have boron dilution accident, for instance. And basically having the reactor somewhat simplified. But when we look into this kind of what we get there, we might even get some new issues. Basically, like passive systems, they are basically always on, or should be, at least if they are like truly passive. So basically, this kind of system can operate in a bit different ways depending of the plant state, and it might also interfere with this kind of defense in depth approach. So where basically you have, for different function, you have a different system. And we don't have that, for a new concepts, we don't have that much operational experience that we can basically outright say that this is not an issue. So we need to basically, at this point, when there are new designs, we need to bring in look this in a very holistic way, including taking into account uncertainties. And also, operation of this kind of system might be very much different from system that is basically based on active system, where you can control system parameters by, for instance, using pumps and so on, instead of you having some sort of passive system that finds a new balance depending on the power level and the system state. There's also issue that many designs have multiple reactors that are basically brought in as modules. So what is the effect of this on many different topics? And yesterday there was quite many questions on nuclear waste handling of SMRs and some discussion. So I think I took liberty of highlighting this discussion also for today. So basically going through three topics that are relatively, well, they are not unique to SMRs, but with the SMR designs that we are seeing, they are basically bringing in some new things to consider. Starting with defense in depth. So basically, show of hands, who has heard of defense in depth? Okay, almost, well, half. Who knows what actually defense in depth means? Okay, so 1/3 maybe. I must confess, I mean, if somebody were coming to me and asking what's the true meaning of defense in depth, I would be a bit scared to tell. So no pressure. Who knows, who can actually tell what defense in depth means?
Can I say online?
Please. Yes?
Yes. Hello, everyone. According to your question, I can say that defense in depth is use of successive barriers against the accidents that can happen for a power plant, and use of different methods based on mitigation and prevention.
Yes. Basically, yeah, and you were referring also basically to accidents and then the basically barriers. So there is basically this kind of like, well, yes, defense in depth is basically the idea that if you have one like barrier to an accident or a bad thing, it might fail because there are always some holes. So you must have successive different levels of control and eventually mitigation against bad consequences. We have systems that rely control the normal operation. We do need to have systems that if something off normal happens, bring the system back to normal operation. And if this fails, we need to have systems that control that accidents do not cause any damage. And even if these systems fail, we need to have systems to control for the damage of these accidents. So basically, we have successive barriers. And this is basically also kind of these levels, and different levels. Also, basically remembering that we have 3 high-level safety objectives. We need to cool the core, we need to control the criticality, and we need to keep radioactive substances out of the environment. So basically, defense in depth applies to all of these, and it also applies to other things. We have do we have Nadia in the audience? Yes, we have Nadia in the audience, who has been working on institutional defense in depth. So I think she will be also telling tomorrow about this kind of thing. So this is not only physical barriers, this is not only safety and control systems, but this relates also to how things are organized and so on. So this is basically from some IAA. So basically we have the different levels of defense in depth. We want to prevent abnormal operations and failures. We want to control these abnormal operations. we want to control accidents that are within design basis, and then we need to control basically if there's something that happens beyond the design basis, beyond the basis which the plant has been designed to endure, what kind of things and severe accidents, which is basically saying that the core is starting to melt. And we, of course, if everything of all of these levels fail, we must be able to mitigate the consequences of this radioactive release. It might be, or these are like functional, but these are also like physical, like for instance, the barriers for radioactive release. Uranium dioxide rods and the cladding, which is two first basically physical barriers. I always want to talk about physical barriers because this is what fuel is what I've been researching all the time. So and then of course we have the steel pressure vessel and containment and so on. It has basically defense in depth. It has basically this is a picture taken from the Canadian regulators webpage. So this is basically like if we are looking at these levels of defense in depth, there's like we can say the objective are and basically means of control. We have the normal process systems for normal operation. Then we have the protection systems for control of abnormal operations and control of accidents. And then we have some design features like core catchers and so on to mitigate severe accidents. And of course, in the end, we have the off-site protection, like emergency planning zones and emergency plans on what will happen if there is a release. And so basically, and all of these systems and these measures should be independent and not interfering. But with the passive systems, then there is this basically question that if we have like passive system that is always on, that basically failed at this point. So it's still active here. So do we count on it, or do we basically count on it acting adversely towards accident mitigation, or what happens? And of course, we need to figure this whole thing out. And especially also, since we are looking at the whole plant situation, how activation of one system affects to the functioning of other systems. So basically, this is of course the discussion that we see that there are like SMR designs that first proposed that have innovative features, and then when they start to make this kind of process of designing and analyzing, they have noticed that, okay, we need to rethink this particular feature and this particular strategy. And very often it's related to how basically this kind of independent defense in depth system works. So I put some pictures on SMR designs that have been published year by year basis. So this is a new scale picture from about 2015 or so. And this is new scale from 2019. So now a question. Can you spot the difference? What has changed?
There is a passive condenser for decay removal.
Yes.
The reactor pool.
Yeah, reactor pool has changed. Okay, but you can see here decay heat removal passive condenser, which is basically it's coming from taking heat from the secondary circuit and putting it into the pool. So basically it's cooling from the secondary side, and it's basically as it reads, it's a decay heat removal system, so it's used for after the reactor has been shut down and there's no more steam going to the turbine. Early on, it wasn't there. So I don't know if anybody remembers what was the strategy of NuScale after the basically beforehand for this decay heat removal. Basically, originally, it was so that they just opened these valves and had the natural circulation through the wall go natural circulation and cooling to the pool. So basically, this was just another way of putting the decay heat into the pool. This was also a way if there was some sort of overpressure accident or some other accident to basically ensure the cooling. So, can you guess or speculate why they wanted to include these separate decay heat removal systems that, of course, increase the number of penetrations to the vessel walls and increase the complexity of the system? I mean, we want to have simple systems. Why we are increasing complexity? Okay, how does it increase the safety?
Adding another system?
Yes, but if you think about okay.
For the secondary system and the valves on the rated pressure reservoir more for the primary system. So, which is an accident for both sides.
Can you basically repeat a bit louder?
The decay heat removal system is especially for the secondary system. So the vent valves on the reactor pressure reservoir more for the primary system. In this way, we prevent accidents for both sides.
Okay.
Please also Alireza online. Alireza, please.
Is it related to the level 4 of defense in depth and including some other passive safety systems which can cover the design basis accidents and over?
Yeah, indeed. And basically, like if you think about this system, breaching this, like opening these valves, and in case of accident. So this is basically the accident system. But basically, when you shut down the reactor, it's a normal operational procedure. So basically, in this original way, you're basically putting your reactor into an accident mode every time you basically shut down for refueling. And if we think about, if we think about defense in depth, you're basically supposed to be in this kind of normal operation, and then when you shut down the reactor, you're just suddenly there in the accident mode. And that's not necessarily a very good idea. So basically, one potential reason would be that these have been included so that you have indeed this basically one like a normal function for a normal operation, and then if these fail, you will have for the accident situation, or you will have this another system. So you have multiple systems that and they are diverse systems that you can use to ensure that there will be no accidents. Okay. Are there other problems with opening these valves for core cooling? If we think about, I went through the physical barriers of radioactive release. Anybody remember anymore what they are?
The 5 physical barriers.
5 or 4. Yeah.
The first one will be fuel matrix.
Yeah.
And then it will be the reactor coolant, the reactor coolant system.
Yeah, the primary vessel.
The primary vessel. Then
Contain.
the whole coolant thing, and then the containment itself.
Yeah.
And then the steel lining of the containment building.
Yeah. So when we open these to ensure core cooling, what are we actually breaching when it comes to physical barriers?
So we see that there's the 3 barriers and then we go to the 4th.
Well, we are hopefully still having a few intact, but we are like destroying one of the physical barriers to ensure core cooling, which is basically we are ensuring one safety objective by diminishing the layers of defense in other safety objectives, which is, of course, something that we actually don't want to do. So basically, increasing complexity and by installing or designing decay heat removal systems is very justified, because then we have these kind of like independent systems and systems that do not like endanger other safety objectives. This is Hitachi's BVR X300. This was a picture from a year or 2 back, and this is something I saw this year. So, I mean, there are some auxiliary and some other systems pictured in this picture that are not shown here. And this was supposed to be showing all the safety systems. But can you spot a safety system here on the right in the new picture that's like missing on the left one? Yeah.
The core capture, maybe, if there is.
Yeah, there seems to be probably some sort of core potentially something here. I'm not sure. I don't know if there's a core capture. It might be, or some sacrificial material, but it's not like named. Yeah, please.
Or an injection system.
Yes, indeed. So I think yesterday there was this discussion about non-boron systems, and I believe that originally, if I have heard correctly, originally at least BVRX 300 was not supposed to have the boron system, at least for the reactor shutdown, but having some other way to ensuring the reactor shutdown. But now there is, so basically it's a boiling water reactor, so it's operating on clean water, so there is no boron in the normal operation for basically boiling water reactors. So, but in many or all BVRs, there's the boron, secondary boron shutdown in case the control rods do not work. So for boiling water reactors, there's boron only during the accidents. So it's an old joke that for a freshwater water operator viewpoint, boiling water reactors are always in a transient mode because there's boiling. And for the boiling water reactor operator viewpoint, the pressurized water reactors are always in accident mode because there's boron in the primary circuit. But anyway, so why, okay, I probably already said, but why did they have to include boron injection system? Yes?
This accident when our control laws are not available, we are able to use this.
Yes. Yeah. So basically, like, just in case the normal system for operation fails, we don't want to go into a real accident. We need to have a system that ensures that this off-normal situation does not progress into an accident. But then we just use the boron. So basically, like, this kind of like consideration for redundancy and for this kind of like adhering to defense in depth will increase the complexity of SMRs, even if we are saying that we want to make very simple cases. It's still like basically this whole BVRX 300 like safety system that there's, for instance, there are like increasing these kind of like spargers and systems for the containment, controlling the containment space, but it still like relies on the idea that there is basically very robust connection between the main steam line and this reactor pressure vessel that does not break like on this side of this main isolation wall. So basically, and this is something that whether the regulator will accept that this part here will not fail is something that I'm very interested in seeing in the future. That whether this justification for this part is sufficient, but it remains to be seen. Some other things, of course, when we have multiple passive systems in the same place. So basically, when we are starting to assess this kind of system, we want to verify the safety requirements and verify the defense in depth level and the independence of individual defense in depth level. But basically, when we are looking at the thermohydraulic, for instance, performance, there are uncertainties on many levels. There is the phenomenal level. So can we actually know what happens in very specific places, very specific conditions and so on? I believe many of you people have been studying on this kind of thermohydraulic phenomena. Then we have this kind of system level for individual safety systems. How do these safety systems work? And there is some uncertainty to that. But when we go to the full plant level, there is also uncertainty on how these different individual systems work and interact in all of these different spaces. So my colleagues in this ELSMOR project have been like looking into this interaction, especially on this kind of like how to actually gather all of the effect of all of these lower level uncertainties. And when you have the whole system where basically everything affects everything, what happens there? So basically they have been looking this kind of like requirements elaboration. When you have the high level requirements that implementation of defense in depth in SMRs must be tolerant to uncertainties, then you have the whole system. then you need to have all the specific subsystems or specific subparts of the system architecture must be tolerant to deviation in activation and actuation and operating parameters. And all of these specific systems need to be also tolerant to deviations from predefined system configurations for the activation and performance. And this kind of like deviation from basically this what happens with when all of these uncertainties combine, and when these either with the actuation or operating conditions, and when you might have, for instance, a valve that even is not, for instance, closing fully or opening partially, what will happen in the other parts. So if you have some like additional uncertainty, and everything needs to be taken into account in this kind of like analysis. But this is like still work ongoing. Away from the defensive depth. Okay, I'm losing time, sorry. So basically, we have also multi-modular units. Some SMRs have several units in the same reactor. So basically, we are sharing equipment. So basically, we are sharing space. So there is a big issue of what happens when one unit malfunctions or fails. With Fukushima, we already saw that accident in one plant had an effect on actions made on the nearby plants. Now we would have the reactors potentially in the same room. And these are the issues. There's also like a whole issue on probabilistic safety analysis, and of course like complexifying the idea that usually you have the PSA level 1, which gives you core damage frequency, PSA level 2 telling you how much radioactive release happens, and PSA level 3 on the environmental effects. What happens when you have basically, plants in the same vicinity? These SMR modules are supposed to be constructed and sent in place. It will be something that, for instance, in factory, they need already to be tested in like realistic conditions, because you cannot just test one system and say that, okay, we know how all of this works, because in passive systems, everything basically affects. So you need to have this kind of like integral test. And basically you will need to, the plant operators will need to understand the integral behavior of the plant, instead of like being able to say that, okay, we just, we need to, according to procedures, we need to operate this plant or something, but because the flows come through the physics. Basically like 3 Mile Island happened because the plant operators did not correctly interpret the plant state and made the wrong assumptions. And with the passive systems, it might be even harder. System dependency might be more complex than with the active systems. And if the plant safety systems have also active components, there is like the question how well the automation interprets the passive plant system. So there is might be challenges to human-machine interface design and procedure design for monitoring and secure passive systems in a potential issue, because we have so it might be a non-issue. It might be that passive systems always go to some stable state, but as of now, we cannot make this statement unqualified. Of course, if we have many units and one control room, every unit might be in a bit different operational state. They might share support systems. and might be concerned by the same event, for instance, large earthquake and so on. And because they're bits in a different state, might have different consequences. So basically, we have we need to take into account that if we are running the same thing from the same control unit, control room, there is a risk of unit confusion and mixing, and we need to, all the control operators need to be able to always say that, okay, this signal refers to this unit, and so on. But this is, of course, easier if there are like long these kind of grace periods when you can actually like step back and look and not get named action, which is basically also the point of passive systems. But anyway, since we yesterday discussed quite a lot of radioactive waste, I just wanted to just have the last discussion on that. Of course, like the point is that always radiological waste must be handled responsibly, and basically, like we heard yesterday, waste streams from large and small units using or reactors using the same technology are relatively similar, but they might have some quantitative differences. And waste management and decommissioning is something that needs to be planned from the beginning. As a reminder, basically when we are talking about nuclear waste, we have a wide variety of waste. We have spent nuclear fuel, we have intermediate level waste, which is processing, cleaning resins, irradiated structural components, and then most of the stuff is low level waste, which is like used clothes and contaminated tools and so on. So, I mean, when we are talking about nuclear waste, what is this part which worries you the most? Or what do you consider the problem?
The high level waste.
Yeah. Usually people consider the high level waste. When we talk about like how much and what kind of waste there is, people need to understand that most of the waste produced is like non-issue, because we can like put it into, well, this is a bit contaminated. We basically need to put it somewhere where it does not interact with the environment, and it doesn't pose danger, but we need to have, well, I mean, this needs to be taken care of, but this is a bit harder to take care of, and this is the most issue. Fortunately, it's the smallest in volume. It's basically a large nuclear power plant produces like 50 tons of waste annually, which is like something that, I don't know, fits very well on that podium. And even here, like speaking as a Finn, so we have this Posiva facility for final disposal under construction. First tunnels for the disposal have been just constructed, and they are supposed to be start operating in a couple of years. So basically, this kind of geological disposal, it's a done deal. For decommissioning waste and maintenance waste, there's like a lower, like 100 meter below ground operational disposal facilities already operational in many places in the world. So when we, for instance, discuss the decommissioning waste, this is basically like the amount of stuff that will be coming from a large power plant. So the volumes are rather small. When it comes to high-level waste, we need to, of course, get these kind of facilities in many countries, but the SMR fuel is still relatively similar. When we think about this kind of like, for instance, NuScale, many modules and spent fuel pool in the same place. So basically, we need to acknowledge that basically smaller cores are inherently wasteful, because they leak neutrons, which means that you either have lower burnup or you need higher enrichment to reach the higher burnup. So for smaller burnup, there will be higher amount of actinides in the fuel compared to a large core, and if you have higher initial criticality of fuel assembly, you increase the impact of core loading error, and there's also other issues with increasing in fuel enrichment. Of course, because it's wasteful, there's an increase in the remaining reactivity of the fuel assembly, which might need to be which must be taken into account when doing criticality assessment. But this is something that is being done in this kind of like assessment all the time. And of course, with the reactor and spent fuel, if the pools are in the same place, it's basically we need to take into account the interaction between the spent fuel and the cores. If we basically, like yesterday, it was the discussion that if there, like basically, if there for the SMRs, SMR fuel, if there are more actinides like plutonium, what's the final effect on the final disposal case? This is once again from the possible safety case, the amount of radioactivity that comes to the near field. And as you can see, it's basically dominated by the fission products. Why does not, basically we are always hearing about plutonium. Why does not plutonium figure in here? Any guesses?
The half-life of the plutonium is much shorter than the non-zero speed.
Well, half-life of plutonium is still, this is like million years, so half-life of plutonium is here. So if it would be, so it's not, basically the reason is that it's not coming out. It's basically like a heavy metal, and even if there's water inflow, it does not move that much. So basically, if you look, this is like a carbon, chlorine, iodine, so this basically forms salts, and well, cesium probably also, and nickel. So basically, these are things that are water soluble, that go with the water influence. And that's why in, for instance, this final disposal safety case, they are relevant nuclides. Like heavy metals, they do not flow with the water so well. So this is basically for the reason that I'm personally not too worried about that there might be a bit more plutonium in this spent fuel of light water reactors, even if when compared to light water large ones. So basically, this is well, just an example of one difference in the spent fuel that's potentially a non-issue when you look at the final disposal safety. For decommissioning, we have the compact reactors, which might be a bit difficult to start cutting up or dismantling, but you can also try to create a situation where you can take all the irradiated parts and just like remove that part and decommission. There's basically potentially have sealed modules like this new scale or these microreactors that plan to have this whole module just like removed and taken to decommission. And this, but this of course needs to be thought through from the get-go. There's also like an aspect that if you have many reactors and you have started one reactor 10 years ahead of another, maybe you need to decommission the one reactor there. And so taking into account these organizational issues. I have been working with the basic heating reactors, and there basically you want to put your nuclear facility next to the community. And this kind of like places are usually very valuable land estate. It's also similar approach if you have an industrial reactor, which is like next to the industrial plant. The land area is going to be like valued. So when you start to decommission, you want to do it quickly because you don't want to waste money on land that just like sits there. So this is also something that these are aspects that need to be taken into account when designing the reactor, how you're going to decommission it. So it's like decommissioning by design. IAEA has already ongoing program also on that. But okay, so we went through some of the specifics of light water reactors when it comes to the design and like operations that we have been working on within this work package 2. Work package 2 had or will have in total of 12 different technical reports, which any one of them would take at least 1 hour to go through. So I'm just like highlighting some of the very specific issues for SMRs. So, but thank you for your attention and participation. So if you have any questions, please, I think we have some minutes time.
Thank you, Will. Questions even from the people that are online, obviously. I will take care of your hand raised. Is one question?
Please, there's a, yeah.
Thank you for this informative presentation. And I want to just a clarification. When you say that the modules might be in different operation states,
Yes.
what do you mean by different operation states?
Well, I mean, basically, we might have, if we have like 4 modules, we might want to operate them so that the fuel reload is, for instance, at different times. So we might have 2 modules that are operating currently, operating one that's being raised up to the power and one that's being shut down at approximately at the same time. Or if there is some issue with one reactor that you need to reduce its power, like to 60%, one is operating at a lower power, and so on. So there might be, and in the future, for instance, NuScale has said that their reactor can operate with highly variable renewable grid. So you would have several units operating in load following mode. Maybe the
Yes, there is one question from Hamed. When several SMRs are to be operated in a single power plant, is it required to have multi-control rooms and operators?
Well, for instance, NuScale is proposing that they would be operating all the reactors from one control room. So at least they are proposing that there would be a single control room. I do not know what's the situation on the interpretation of whether this will go through or not.
On this topic, if I may add a comment. On this topic, some years ago, we started discussing in IAEA, during the working groups for SMRs. And I was personally a little bit concerned about the possibility to have to control multiple reactors from one single control room. Because I was thinking, oh, come on, but if something is happening on one module, people become, let's say, concentrated on that. We may have some human factors transported one. And probably Sean can give us an answer. Our Canadian colleagues say, oh, come on, but we are managing multiple reactors, multiple large reactors in one single control room since decades. Where is the problem? Sean, am I correct?
It is true. So we do 4 large reactors in one control room. Human factor people, we have very good human factor people that have looked at all this, come up with all the scenarios, but at the end of the day, we say we done it quite safely, we demonstrate that. So
Yeah.
I know it was a huge concern for NuScale. I was actually at the facility and we through some scenarios. I think, you know, at a high level, their system looks very good for controlling those. Even an important note is there's very operator actions are credited as important to safety. And that's how.
Yeah.
So even one operator can do, I think, 4 reactors. So the idea is for a new SMR facility, you want very bored operators. And then you have to try to figure out how to keep them engaged. That's a separate problem. But from our perspective, we've been doing it for years, and we've done this.
Yeah, I think that this is very much like relates also to what is the experience from prior things like for load following. In Finland, we have been like concerned about potential for load following, and then when we go to France, they are saying that okay, we have been load following for decades and no problem at all, and it's like okay, yeah. I think you were raising your hand first, and then we have comments there.
I have a question related to the load following.
Yes.
If they are planning to do it by managing the single reactor or the cluster of reactors, because as you said, in France they do it, but also in a cluster way, not managing the single one.
Well, I'm not sure about how it's going to be planned, and probably it will be defined in the like operational safety guidelines. That what's the strategy, and but I'm not sure if it has been. I mean, NuScale is showing that their individual plants can like basically do the reactor load follow, and then they can do turbine bypass. So they have different strategy for, but what's the actual like operational way of doing that? Most likely, I would assume that similarly to France, that they would be varying the reactor which one is responsible for load following, depending on what is the burn up and what is the frame of the cycle, because you cannot load follow so easily at the end of the cycle. But please.
I just wanted to ask about forum. Are you avoiding it in the control only in PDRs or in PDRs?
Well, so basically, like now we have, for instance, Nuvard, which is looking forward on non-borated operation because it reduces the waste and it eliminates some accident modes. So, but see, there are some potential issues when it comes to non-borated operation of pressurized water reactors. But please.
Ones related to common control rules. The Dublin case in Canada is for reactors, but sounds quite demanding. They do scale, common product, they kind of reduce this stuff. And then this one case, simply the Chinese thermal reactors, they have 2 reactors, and if I don't know, they use 3 operators, one for each reactor and one for power, because they have one we want power for 2. So there are different things.
Yeah. Basically, I think that required operator actions and the time that you need to do these operator actions are very relevant on how many operators you will eventually need. If you have some large reactor where you need to do actions like on a faster time scale, then you will need to have some person there being ready for action all the time. Basically, if you have this kind of very inherent reactor that's very easy to control and needs only few actions, then you might be able to handle this situation with less people.
Were you considering changing properties of the pool water to control power or this?
Sorry?
You have properties of the water in the pools where the reactors are located.
For example, you were showing that we have the heat exchange with this. For example, we change some properties of this water to control on the power, on some safety.
Yeah. You know, like of course the pool water defines what the efficiency of heat exchanges. But for instance, if most likely you will want to have the pool water relatively close to room temperature if you are going to have kind of like a hallway where there's operational people doing operations, so that you actually don't have much leeway in the temperature of the pool. Other people just for the you have workers on top of the pool, like needing to do work. So basically, it's his temperature you want them to work on.
Okay, thank you.
Thank you
very much, Bill. Thank you, Ahmed, for the question. Thank you to everybody. Now, I see on the screen that Bernard is here. So Bernard, you should be able now. I gave you the right to share the presentation. So if you want to try to share.
Yeah, I will try to do that, Marco. So is it working?
Not yet. Let us wait some seconds.
Marco, is it working?
No, we cannot see the.
Do you see my screen? You can see the presentation. Sorry.
Otherwise, if you prefer, I may, since you send me the PDF file.
Yeah, I'll try.
Yeah. Something is, okay, we see your screen. Oh, it's good.
Is it okay?
Yes, if you put in, is it a PDF file, right? If you put in presentation mode, probably we can see.
Sorry, I will remain like that because I am on my iPad. I have a connection issue.
Okay.
So sorry, it's a little bit. But
No.
I will try to do it like that, if you don't mind.
Oh, no, it's okay. So let me introduce a little bit you. Bernard Salah is the president of the European platform on nuclear energy. The name is SNTP, so Sustainable Nuclear Energy Technology Platform. So it's an organization that is collecting all the stakeholders, industrial stakeholders, research, education. So all the people that are involved in the nuclear sector in Europe are more or less belonging to SNTP. And Bernard is chairing, is the president of this important organization in Europe. He's also working in EDF, so he's directly involved in the nuclear business. And he will share with us an important point of view on what's going on in the nuclear area in Europe. What are the potential, what is the potential future of nuclear in Europe, with a focus obviously on the SMRs. And you can see from the title that the SMR partnership will be an important initiative today and for the future, also for SNTP. So thank you once more, Bernard, for having the time to be with us today. So I leave you immediately the floor. Thank you for coming.
Thank you, Marco. It's so my great pleasure to be with you. So sorry, remote. It was not possible to be with you in Milano, but I will try to give you an overall view of SNETP on the one hand, and then on the SMR partnership. I'll try to go through my presentation in a relatively rapid way in order to let some room for questions at the end. So perhaps to begin with, the overall vision of the nuclear landscape in Europe seen from SNETP. So in fact, today we have really in Europe by 2021 a huge amount of activity dealing with nuclear. So you see the number of 104 nuclear power reactor, which represent more than 50% of carbon-free generation in Europe. We have a global turnover of activity of 100 billion euro, 1.1 million jobs, research reactors, and also many applications. It means that nuclear energy probably in Europe is one of the most important internal one. By internal, I mean that most of the activity and most of the supply, most of the industry and most of the research is done in Europe. If we look at the landscape by 2050, in fact, in all EU scenarios, you may notice that a significant part of electricity is going to be provided by nuclear energy. So it is roughly speaking about 15%. And whatever the debate we have at this moment about taxonomy, and you probably know that there is a very important vote today in the Parliament, nuclear is to play a role in this landscape because it brings carbon-free power, because it's flexible, and it can be used also for hydrogen generation and for also industrial heat and many other applications. We have also the question of SMRs and generation 4, which is emerging. I'm going to touch that. And about waste, which is also a very key question. You probably know that in Europe at the moment, we have really significant achievement. Let me quote what's happening in Finland with the opening of a new waste depository, what's happening in Sweden also on which there is a project ongoing, and with a very soon opening also of this site, and also in France, on which we have also a depository not so far from Reims in Bue area, which is going to be open. So in fact, we have a future for nuclear in Europe. Whatever some I may say, the politician and the policy may speak, and there is an important issue to invest on training, innovation, in order to support this vision for nuclear by 2050, and that's one of the goals of SNETP. So as Marco was explaining, SNETP is in fact the European platform linked with research about nuclear energy in Europe, research about fission, nuclear fission. It's not fusion. So we gather more than 110 members coming from either research organization and also industry and academia. So you see the small camembert on the right-hand side of my slide. And we are organized around 3 main topics. In our organization, we call that pillars. So you see on the slide, which are called Nugenia, NC2I, and ESNI. So Nugenia is mainly dealing with generation 2 and 3 reactor. ESNI is dealing with generation 4 to make it simple, and NC2I is mainly working about cogeneration reactors. That's to say, activities which does not generate electricity only. Of course, all these three types of activity are closely linked because we have many common factors. Let's take the example of R&D infrastructure or simulation code and tools, for example. There is in fact a continuity between generation 2 and 3, between generation 4, and between cogeneration reactor. So what I'm going to do is to describe very rapidly the vision of these three pillars. So to begin with the question of Nugenia. So one of the key priority of Nugenia is what we call LTO, so long-term operation for existing nuclear power plant. So I was explaining that we have on the grid today in Europe 104 nuclear power plants. So they are of utmost importance to operate those plants, of course, in a safe way and on the long-term way. They can provide also flexibility on the grid, and given the crisis we are living at the moment, they are very important pillar for providing electricity on the European grid. We need also, in order to support, in fact, this fleet, a European-wide industrial-driven nuclear R&D program to maintain, in fact, nuclear competitiveness and safety. And also, in order to take into account the future and the other topics which are emerging at the moment linked with the existing nuclear reactors, such as clean heat, such as hydrogen, not forgetting also health and questions like manufacturing. About the innovation priority, three main topics. First is innovation and competitiveness. I'm going to come back on that. Second is digital transition. And third is safety and environment. About ESNI, so ESNI is driven by looking at, let's say, far future, or in fact, a future reactor of generation 4. We have significant activities in Europe in that respect, with many concepts and even reactors which have been developed. So on the slide, you have 4 of them. MIRA, probably know MIRA. MIRA is in fact a project of lead-based accelerator-driven system to be built in Belgium, in the SCK CN in Mol. You had Alfred with the lead-cooled fast reactor concept. You have Allegro with the gas-cooled fast reactor. And last but not least, all the work which has been done, so mainly in France, but also in Italy, about sodium-cooled fast reactor. The idea of these reactors is that they could help to make nuclear more sustainable than it is today. The key question is, when is the first demo project to be connected to the grid? So we have many debate in that respect. We took the date of 2035 for this presentation. 2035 is the date which is announced by our colleague of SCK CN for the MIRA project. About NC2I, that's also a very important topic. So to produce hydrogen, but also to produce high temperature heat. You probably know that if we want to fully decarbonize our world, we need to decarbonize industry. Industry is needing heat, and especially high temperature heat. It's very difficult to provide this high temperature heat through heat pump. So today it's mainly provided by gas, natural gas. So nuclear could be a good solution in that respect. And by the way, heat temperature reactor, as the one I was mentioning before, could be a good idea in that respect. So Poland, for example, is working on this topic. They have a strong project called ETHER, EU Thermal, which could be a solution or at first an idea or concept in order to provide heat on the long run. So this is the global strategy of SNETP. So to work on this three pillar in order to contribute to the energy mix of Europe, as I was mentioning, something like 15% of the global electricity, which could be provided by nuclear energy. We have to work on the three topic at the same time, and I will try to explain a bit after how we see the global approach. So on this slide, you have some idea about how we see, how we understand the global strategy for nuclear in Europe, and especially the question of light water reactor and the question of generation 4. So this point is mainly focused on what could be the different steps. In fact, we have the ideas that there are two main paths to be followed in parallel and perhaps not exactly at the same speed. So the first idea is that our key point as energy player is to reach net zero by 2050. That's a huge goal which have been set by the EU Commission and in fact by a lot of countries all over the world. In that respect, we believe that nuclear reactor could play a significant role in order to achieve this goal. And if we want really to be ready, we need in fact facilities which would be developed in a very soon and very nearby future. And so that's why we think that we need to go on with long-term operation of existing nuclear power plant, as I was mentioning before. And we need also new generation 3 reactor. And for this reactor, we believe that the only technology which could be available at an industrial scale and built in great quantity before that date of 2050 is the technology of light water reactor. So both big plants, but also small modular reactor. So light water reactor, first priority, first path for the future. Nevertheless, we have to take into account that we need to have nuclear energy sustainable on the long run. And for nuclear energy to be sustainable on the long run, we have to cope with two key elements, which are the question of waste, and especially long life waste. So we need to reduce, in fact, the volume of those long life waste, which are produced by nuclear energy. And the second question is about the resources on uranium fuel. So you know that the resources of fresh uranium are limited. The figures, well, are around 100 years, 150 years, something like that. And we have to cope with this question, and so we have to recycle. And if we want to deal with those two elements, so long life waste on the one hand and recycling of the fuel on the other hand, the only solution is in fact generation 4 reactor and AMR, what we call AMR, advanced modular reactor, so fast reactor, fast breeder reactor. When? So of course you know that we have no industrial project at that time of this technology, of different technology belonging to the AMR family. We believe that first demonstration project could be available at the soonest by 2035, given that the TRL level at the moment is relatively low, and that commercial project, by commercial I mean really industrial developments of this project, could be available, let's say, around 2050. Even if those two paths are a little bit different with different time schedule, in fact, we need continuity in this different policy because, in fact, the knowledge, the research, the facilities, the people, the training, there are huge synergies between these different aspects, and we need to work on both of them. So that's the overall idea on how we see the future. So let me now go on the question of the SMR partnership. So the SMR partnership is in fact a global idea which has been set by the EU Commission in order to push and to help the development of SMR in EU to start operation SMR, which could start operation in the year 2030s. So the main goal, in fact, of this partnership is to create a sort of global vision and to create, and that's the important words, enabling conditions for different EU SMRs to be built in, let's say, a short horizon. So the idea is to develop the necessary industrial supply chain in Europe, to encourage the implementation of common or at least harmonized licensing process across EU. That's a very huge and important topic, this question of harmonized licensing. You know that the strategy of SMRs, so you all know SMRs, is in fact to build numerous identical projects. So if we want identical SMR project to be built in Europe, we need in fact to have harmonized licensing, otherwise we are going to create differences between these projects. So harmonized licensing is really a key element, not easy element, but a key element. We need also, of course, a strategic research agenda, both on light water reactor SMRs, but also on AMR generation 4, in order for them to be ready. And last but not least, we need also to understand what is really the international marketing strategy of the EU SMR value chain. So this partnership has begun. In fact, it has begun. It has been launched during a first EU workshop who occurred on the 29th of June, which was organized by the DG Energy, so the European Commission. And you see with a lot of participants, 110, 22 member states, and with a proposal, including a proposal for a European SMR partnership. So we have begun to work on this field. In fact, we are already organizing these activities with a steering committee, launching and managing, in fact, this pre-partnership. So the idea again is to identify the enabling condition and also constraint in order to have a possibility to build SMR in the next decade in Europe, with the different objectives I was mentioning: industrial supply chain, harmonized licensing process, research agenda. How is it organized? So you see the different logos. So it's something which is composed of the EU Commission, and in fact the DG ENR is leading, in fact, the field for the EU Commission, coordinating all the other bodies of the Commission, RTD, GRC, and SREG with the Association of European Regulator. So, which is a very important point for us as we want to have harmonized process. Foratom, so Foratom is the association of the nuclear industry in Europe. So you probably know that it's changed its name and it's now called Euratom Nuclear Europe. And it's an ETP, so the platform for research and innovation in Europe. So the goal of this steering committee, I'm not going to go into too much detail, but you have here the key ideas, is in fact to organize and to pilot somehow the work of different work stream in order to define these conditions, these famous enabling conditions for the future of nuclear SMRs in Europe, and also interact with the different stakeholders on a regular basis, stakeholders belonging to the European Union, but also stakeholders which could come from abroad, abroad being UK, for example, but US, Canada, and also international organization, NEA or IAEA, for example. So let's go perhaps in more detail about the different work stream of this partnership. So the first one is the market. So the idea of the market is relatively simple. That's to try to understand what is the EU market for SMR at the moment. So you see there is a clear program. What are the tasks to be done? Literature analysis, a global survey about the different bodies which could be interested for nuclear, and something also tax-free, which is very important, which is to understand the sustainability criteria to be considered in the market. So you see that it's under the responsibility of Euratom, that there is a share coming from Tractebel, and then there are different participants coming from different companies or research body. So you are going to see a very similar organization on the other work stream. The idea is really to create a global coordination. Licensing. So licensing is something very, very similar, led by ANSREG, so the Association of Nuclear Regulator in Europe. The share is coming from the French Safety Authority, so-called ASN. You have the 16 experts from 13 countries, nuclear safety authority, which are going to be involved. And the idea is really to go on about understanding how a common or at least harmonized licensing could be done. It's a difficult topic. What is very encouraging is that ANSREG is really deeply involved in that respect, and we are beginning to understand how it could work, how we could do that, how we could do it on specific project, or how we could do it on specific technology. The third work group of our partnership is about financing. So frankly speaking, this one has not yet begun. The main question is in fact the question of taxonomy. So we are waiting a little bit for the result of the vote of the parliament today. The idea is to launch this partnership in the second half of 2022. And the idea is to try to find a way to simplify or to clarify the financing of SMRs. Supply chain. So supply chain is really key topics. It's work stream number 4. As I was mentioning, we have today more than 1 million people all over the Union who are working on nuclear. So we have really a very important supply chain. Again, nuclear is probably the unique energy industry in Europe for which we have the full supply chain on board. And so we have to mobilize, in fact, this supply chain for the preparation of the construction of this SMR and AMR. So the idea is to identify the key features, to understand what are the specific topics which have to be addressed for SMRs, like code, regulation, way of manufacturing, standardization, possible use of non-nuclear, high quality equipment, the way also of the way under which the construction work is going to be reviewed. So a lot of different topics in order to harmonize and to make the supply chain more efficient in that respect. So in that case, again, the responsibility is taken by Euratom, with a share who is coming from Ansaldo Nucleare, and with several contributors, as you see, and the kickoff has already begun. So the work is underway since early January 2022. About research and development, so I'm going to focus perhaps a little bit on this point because it's a topic on which SNETP is deeply involved. It's clear that we have to define a global research, development, and innovation program, consistent with, in fact, the market needs and consistent with the different technology. So this program is to be set, of course, for brand new technology like AMR Generation 4, but even for light water reactor, there are significant room to place in that respect, because some features of those reactors may be new and quite innovative and need to be proven. The second item we have to work on is the needed facilities to execute this program. So you know that nuclear technology need to be proven before being implemented, and so that means that we need specific facilities in that aspect. You also probably know that in Europe the number of facilities, research facilities, are not so big and they are aging, and so we need to try a way to optimize the way to use them. Third and not least, especially with Marco and Polimi, the question of training and education is key. So if we have a program about SMR, we are going to need new people, new bright people, brilliant people willing to involve themselves in these activities, men and also women, quite important, in order to be the guys who are going to prepare really our future. And so in that respect, we have different contributors coming from different industrial partners, but also research partners. I'm going still a little bit in detail, and then I'm going to stop about that. You have here, in fact, the different topics on which we intend to work. So you see seven topics. So the core and the fuel, the question of the integrated vessel and internal, passive system, severe accident, modularity, human factor, and autonomy. And the point number 7 is what we call use beyond electricity. So that's the question of being able to generate hydrogen or heat through those reactors. What's also important, I didn't mention up to know that topic, is the question of what we call cross-sectorial synergies. It's a topic we are strongly pushing through SNATP and also with DG RTD. So the idea is really to use our sector, our industrial sector, our nuclear sector, to push synergies toward other sectors, and to use also the best of class knowledge that we can grasp from other technologies to implement them in our activities. Take, for example, digital system, which is quite obvious. They could be used, advanced digital, advanced AI, for example, could be used more precisely, more directly, more efficiently in our activities, and especially in this nuclear program. But that's also true for additive manufacturing, for example, or for several other topics. So after that, you see, I just go through the slide very rapidly, but we have really organized a global process so for each of these topics. So you see, with leaders, pilots, and definition of these activities. So the work is really underway. If I take, for example, this topic of passive system, we need, in fact, really to work, because we have not really all the large scale facilities, experimental facilities at the moment, to be able, in fact, to prove the design of certain reactors. We have not yet the code qualification also in that respect. We have some part, but we have not all. There is really a huge work to be done. Severe accidents is, of course, perhaps more classic. Modularity is also something which is quite important, and in fact mandatory if we want to succeed with our new reactor and SMR design. Human factor is also a key topic, and perhaps to finish the question of use beyond technology. To finish with, perhaps, and to give you some key takeaway of this presentation. The first idea, which is quite obvious, but I think we need to repeat it in a very constant way. We need energy, citizen and industry on a 24/7 basis in a safe, reliant, resilient, and affordable way. So this topic, this sentence is quite obvious, but you know the Ukrainian crisis, you know the difficulties we may have in Europe during this winter. It's very important to repeat this idea in a constant way. The second idea is that according to all the analysis, the electricity demand is really going to increase in a very, very significant way. And why? Because electrification is in fact a way to decarbonize through renewable generation and through nuclear generation. And so you see the figures, a significant growth from around 3,000 terawatt-hour today to around 5,000 terawatt-hour by 2050. In that respect, nuclear could help. It's not the unique source, and it will not be probably the most important source of electricity. Renewable is going to be the most important one. But nuclear could provide significant help as it is flexible, dispatchable, and can generate large quantity of low carbon energy without any backup source, without any storage, and on very small territories. I mean, it does not require, like PV, for example, large space in order to build farm. So it is going to bring a significant part. So that I think that those 3 points are really the key idea for the future. SNETP, but with others, of course, could help, as we believe that research, innovation are necessary in order to implement that. So how do you see the steps? So the first step, as I was mentioning, is really to build light water reactor, both big reactors and SMRs. So we have to work on that all over Europe, in the country which are interested and willing to do so. But even in countries which are not building plants, I think that industry, nuclear training, nuclear research can go on and can strengthen. And by the way, that's the case in Italy. So you see the schedule: first, light water reactor, and second, on the parallel path, the question of AMR. Of course, all this is really challenging. We need support from, let's say, all, perhaps it's a little bit ambitious, but a lot of EU member states. Again, those who are deciding or who have decided to build nuclear facilities, but even those who have strong nuclear industry or strong research on academic centers on their territory. We need also an important point to enhance probably our experimental facilities, and we need people. That's perhaps the most important part, and that was also the reason why I warmly accepted the proposal of Marco to present you in the ELSMOR and with Paulimi this presentation. We need, in fact, new people for the future. With it, I think I'm done, and I'm ready to answer any question you may have.
Thank you very much, Bernard. I will immediately room for the question and answer. Let me comment just briefly that a couple of topics that you mentioned in your speech about the involvement of young people and especially taking care of the gender balance. I have a good news to be shared with you that in our summer school, I would say, Stefano, if I'm right, 40% of the people, more or less, are women. So it's a very good number. And about the interest of the young people on the SMR topic, I think that is we received a very good feedback. So, please, the question for Bernard. I have one about the potential role, in your opinion, of the SMRs in the strange landscape of Europe. I was looking at the news, and for sure you know that tomorrow it will be a tough day for nuclear, because tomorrow in the European Parliament at noon, it is planned today. I read Wednesday, but anyway, it's today. So today is a tough day.
It's today, Marco. It's today.
Okay.
It's today.
Thank you. So today is a tough day because the European Parliament will vote in favor or against the proposal of the European Commission about including nuclear in the green taxonomy, nuclear and gas, because this was the original, let's say, deal agreement between France and Germany from the political point of view. But now that the Nord Stream 2 is away, is gone, what will be the result in the Parliament? I have the doubt that, okay, this could be rejected. So if this is the case, what is your opinion about the potential effect on the nuclear sector at large? And the second question is if SMR could play a role in this landscape, so could help in some way to let nuclear become more acceptable from the point of view of the recognition by the citizens, so the public opinion, and also to raise the interest of the investors. What is your evaluation?
Well, we are going to wait for the vote, Marco. Frankly, I'm perhaps a little bit more optimistic of what could be the result, but well, let's see. The debate is really complicated because in the document which is presented to the European Parliament, nuclear and gas are the two topics at hand. So they pull against nuclear, but given the crisis, the current crisis, there could be also people and countries which are against the question of gas. So it's really a tricky issue. Frankly speaking, it would be a pity if this document was not accepted by the Parliament. What could be the consequences? So there could be new negotiation, of course, but it would be really a pity that new nuclear in Europe could not be financed by European partners or European financing bodies. Because, in fact, the principle of the taxonomy is really to define the investment which could be financed or could be held by the European financing community, and the one for which it will be more difficult because they could, as it is written, significantly harm the environment and the planet. So the funny result could be that other continents like Asia on the one hand or America on the other hand could finance nuclear project in Europe, or could help to finance, and it would be more difficult for European banks. So that would be, frankly speaking, a very sad story. But well, let's see what's going to happen. I do believe that there is some room for nuclear energy, as I was mentioning, because it's the only dispatchable zero carbon electricity source. If we don't do that, we will need storage, huge quantity of storage. It will be, frankly speaking, more expensive. And so the affordability for European citizens much more complicated. And also, you probably know that several countries in Europe have decided to launch a nuclear program. So that's the case for France, for example. President Macron has announced a new nuclear program early this year of 6 plus 8 new EPR. So you see something really big. But other countries have also the same willingness. Take the case of Czech Republic, for example. Czech Republic has decided also to build new plants. They have launched a bidding process in this respect. You have similar ideas also in other countries, in Poland, for example, in Romania with a small modular reactor, in Finland, in Holland, and so it's true that somehow the EU should recognize this willingness of some country to go in that direction.
Thank you. We have 3 questions, and then I would like to close reading to you one statement from one member of the European Investment Bank.
Okay.
Will.
Yeah, Ville Tulkki, hi. So just first quick comment on the previous. Indeed, like for instance, USA has this SMR private-public partnership program where they are offering financing, for instance, Eastern European countries in exchange of them using US technology and using US subcontractors. So basically, this is just a way for them to actually get lots of activity and work on the European projects, then which we are basically, Europe is basically handing over if we are not financing these projects on our own. But the question on SMEDP, so you that SMEDP position is that the sustainability of use of nuclear energy relies on future closed fuel cycle in principle. But is there any discussion on amending this, considering that small countries like Finland and Sweden are taking care of the waste by the direct disposal, direct geological disposal, and France, which is the only country with resources for a closed fuel cycle, has now basically put the fast reactor program on freeze.
Well, my point is, and thank you for the question. My point is really to say that we need first light water reactor because it's an available technology. We can build light water reactor. We know very well how to build them. So it's easy to build light water reactor SMRs, even if some R&D is still necessary. About AMR and Generation 4, in fact, they provide a huge opportunity. They provide a huge opportunity about waste and about fresh fuel. It does not mean that all the fuel is going to be recycled. That's obvious. But nevertheless, it could be a way to recycle a part of it. And about waste, exactly the same. It does not mean that we are not going to have any waste. It would be crazy to think of that. But we are going to reduce the waste. Take the MIRA project in Belgium, for example. Of course, it's a prototype, it's a concept, but the idea is really with this project to try to reduce the amount of actinides. About the French sodium cool reactor, in fact, the project has not been cancelled. It has been postponed because we don't need this project at the moment. The resources in uranium are, let's say, yet big, and about the fuel, the waste storage, we are building a final depository. But at the long run, France policy is still to what we call close the cycle. So that's to say to recycle the fuel, and we do need fast breeder reactor. And well, we have some experience about sodium cool, and so we believe that sodium cool fast breeder SMR or big reactors, by the way, could play a role. But you have other technologies. You have several companies who are working on lead cool fast reactors. So that could be also a way to recycle uranium and to reduce also the amount of scale. So in fact, those AMR reactor are a tool, an important tool for the future. It does not mean that we are going to use them or to operate them on a mandatory way. It does not mean that we do not need any longer any repository site for waste. We need both solutions, and we need to use all the solution together.
Thank you. One question. Please come here so you can talk loudly with Bernard.
My question is why the EU does not focus on only one design, one SMR design, to allow for mass production?
It is a very good question, a simple question, but very good one. There could be several answers. One of the answers could be that the needs from the different country or from the different utility could be different, which could explain why the requirements are different. Other idea could be also that it's very difficult to launch a global bidding process in a very large way among different member states and different utilities all over the world, Europe, to have only one design at the end. And perhaps in a pragmatic way, you know, Europe is a continent. The EU is a continent. We have 400 million inhabitants. We have a lot of different countries, a lot of different view. And I think it would not be probably very realistic to have only one design built in Europe. I think that there is room for several designs. And well, the way is to make, and that's what we are trying to do through this EU partnership, is to make the room for several designs to be built in Europe, trying to help them to create what I was explaining, enabling condition for their futures. So we are going to have several vendors in Europe bringing their reactors.
Thank you, Bernard. A very interesting question. And my personal view is that, okay, we cannot force at European level to have just one design, but this could be obtained in a, let's say, proactive way, supporting the collaboration among at least some countries to collaborate, to cooperate around one design. This could be, is left to the, let's say, the freedom of operation of movement of the countries in Europe. But I hope that will be the case to concentrate, especially on one design, whatever it is, in order to have to support a cooperation, a real cooperation among the European countries on, in order to accelerate the deployment, the development, to be time to market. So this is my hope, let's say.
That's the most likely solution, Marco. I do agree that you could have, I don't know, 2, 3, 4, perhaps 5 design, which are shared among a set of different countries, 2, 3, 4 countries working together on a design or on a technology. That's the most likely solution that we hope, in fact, to appear.
Thank you. The last 2 questions. One, I would like to move, Hamed, I would like to move your question to Sean, because the question is, what feature is the most challenging in the way for licensing harmonization globally and in the European Union? I would like to give the floor to Sean when he will explain us very soon the experience in not only in Canada but also at the SMR Regulators Forum, where France is participating and other European countries. So I think that Hamed, let us wait for Sean answer on that. But Bernard, one last question for you is from Javier Rodriguez, and he says, do you think that an agreement like in European Union for SNTP to promote SMRs would be feasible also in Latin America? We will see also tomorrow the answer from Dario. But what's about you?
Well, frankly, difficult for me to answer this question because I don't know very well the global landscape of Latin America, but you probably know that Argentina, Brazil, they have already some activity about nuclear. Well, quite possible for them, I suppose, to organize something similar. What I also do believe is that the number of technology that are going to appear all over the world is not going to be so big. So there could be also perhaps some opportunity to share these different technologies also in Latin America, and why not European technologies?
Thank you. Before thanking you the last time, let me share with you a statement made 1 month ago from Nancy Sage, Chief Climate Change Expert at the European Investment Bank. She explained that investors looking for green investment are not eager to put their money into nuclear and gas. But immediately after, she said, we wish to use our resources to focus on the low carbon solutions because the climate crisis is just as urgent as it was before, she added. So I see a huge discrepancy. You are concerned by global warming, by CO2 emissions, and you are forgetting the contribution of the, as you say, the most reliable and non-intermittent carbon-free energy source. And this is an official from the European Investment Bank. So probably we may invest next year, if we replicate the summer school of SMRs, we may invite also the investment bank to be with us to learn something about nuclear and especially SMRs. But okay, this is the mood today. This is also why it is important, this type of initiative to learn, to educate on nuclear and also new technologies like SMR issues, because it is important to communicate and to share knowledge, data, real data, not just ideas or let's say, biases or ideological positions. I leave to you, Bernard, the final comment.
Yeah, thank you, Marco, for this sentence and for your comment. I would say that we have to build a new future, which is very, very challenging. We need all the technology, of course, renewable, but I think nuclear can help. It's not the final solution, that's for sure, but it can help. And again, we need that there is future for young people working in nuclear research or nuclear energy. And there is a future in Europe, in several countries, and I would say almost in all countries, even though those who are not building a nuclear power plant. And let me thank also Marco, let me thank you, let me thank also Polimi for developing this training about nuclear energy. We have had a lot of Italian scientific and engineers working in our facilities in Europe. You know, EDF is, I am also from EDF. EDF is also operating facilities in France, but also in UK. We have a lot of partnership. There is a future. We need young guys. We need young ladies. We need enthusiastic people. We need, in fact, zero carbon, and that's a huge challenge for us, for our future, and for our children. Thank you very much. Thank you for inviting me. I really appreciate this opportunity. Thank you, Marco.
Thank you very much, Bernard, because I know that you have a very, very busy agenda. So you found the time to be with us today. Thank you very much again. Thank you.
Thank you. So,
Thank you.
see you all. Thank you, Marco. See you soon.
See you soon in Italy. Bye.
Bye bye.